Hello friends, welcome to Biosomit. So today this will be the third part of the mass spectrometry series. Today we will learn about how to calculate the mass from mass spectrometry. So there are some steps. So here you can see the step 1. There is a peak value observed in the spectrum, that will be the mass is to charge ratio or mass by charge, and the mass is the mass of the molecule plus protons. So let's say one example. If Let's draw one example. Suppose there are two peaks, peak number 1 and peak number 2. If you can see, there is the value of, let's say, 100, and here is the value is, let's say, 125. So this 100 and 125 are the values of m by z. Okay, so we have to deal with the m by z value, where we can get from the peaks. Okay, but before that there will be some assumptions. So what are the assumptions? There will be so many peaks, but the first assumption will be two adjacent peaks are from the same compound and they differ by only one charge. But before we can calculate the mass of the compound, we must determine the charge state of the two peaks. Like, let's say if these two peaks are adjacent, then for one of the peaks the z will be, if x, then for the other the z will be x plus 1 or x minus 1. The difference will be just 1, right? Difference is 1 in charge. So let's check the second step. The second step is nothing but what I have said just before, that assume that two peaks are related. You have to assume that the charge variants that will be from the same compound, right? And they will differ by a single charge. As I have said, the adjacent peaks, there will be the values of the z will be just, they will have the difference of just 1. Okay, so since we have assumed that unprotonated mass for the two peaks are equal, so from this we can set two equations from the graph and we can solve the mass. How? We will check in the problem. But before that, there is another step 3, that says that use the determined charge state to calculate the mass of the compound, as I have said. So how it will be calculated? There will be one equation. So let's check the equation. The equation states that m by z equal to molecular weight plus n into h plus by n. So you know m by z is equal to mass to charge ratio. Molecular weight, this is the molecular mass of the sample, and we are going to calculate this mw. Now n, this is the integer number of charges on the ions, and h is nothing but the mass of a proton, that is 1.008 Dalton. So before having the solution of the problem, let's again remember the general assumption that in a mass spectrum any two adjacent members in the series of multiple charged ions divided by how many charges? Just one charge, right? If this is the curve, let's say for example, the arbitrary example, so if this peak and this peak are the adjacent, so they will differ by just one charge. Okay, so let's go to the problem. So this is the problem. Here you will be given a graph like this. This is relative intensity versus m by z, and there are some peaks. I have drawn it for in a simple way. Like here you can see the many peaks. This black and this red are adjacent, then this red and this black are adjacent. Like this is the value of 1310.4, this is 143.31.6, this is 1441.3. these are the values of m by z, right? Now the question will be, find out the molecular weight of the sample from this mass spectrum. So now what we have to do, remember I have told the equation, that is formula m by z equal to mw plus nh plus by n, and any two adjacent peaks will be differ by one charge. So let's say if I am taking this value 1431.6, so this is the m by z value, so we can write 1431.6 equal to, we have to calculate the molecular weight, so let it be remain the same. Now n we don't know, and h we know, that is 1.008 by n. So let's take another peak adjacent to it, because we know the n will vary just by 1, right? Or we can take after that, then n will be 2, or I mean n plus 2, but let's take this 1310.4. so for this, what will be the equation? m by z will be what? Molecular weight, same, but this time this is not n. If it's n, then it will be n plus 1 and h plus by n plus 1, so that will be 1310.4 equal to molecular weight plus n plus 1 hydrogen's mass and then n plus 1. So we have got two equations. So let's just subtract solution equation 1 minus equation 2, then we will get the n. Okay, so you can see here 14316 n equal to mw plus nh plus and 1310.4 n plus 1 equal to mw plus n plus 1 h plus. So if you just subtract it, you will get the value of n will be 10 point something or 10, but remember I have told that n will be the integer number. Why? Because it is the charge, it is the number of the charges on the ion, so it must be an integer number, the nearest integer number. So from n we can get molecular weight. Let's put the value of n in equation number 1, that is 143.31.6 equal to molecular weight plus 10 cross 1.008 by 10. So we will get the molecular weight, as 14305.9 Dalton. So this is the way we can calculate the molecular weight of any sample. So let's just recap it. You will be given a graph like this. This is the mass spectrum, and you will be asked find out the molecular weight of the sample. So we have to take any two samples, any two peaks. You can take the nearest peaks because one will be n, then the other will be n plus 1. And if you are taking this 1193.1 and 141, so if it is n, then it will be n plus 1, it will be n plus 2, and you can make the equations like that. Here I taken the values of 1431.6, that is n, that I have denoted as n, and 1310.4 for that will be n plus 1. So the equation is, the formula is m by z equal to molecular weight plus nh plus by n, and the next will be m by z equal to molecular weight plus n plus 1 h plus by n plus 1. So what we have done, just we have calculated the value of n from these two equations, and we put the value of n in the any of the equations, or 1 or 2, and we will get the value of molecular weight. So this is the way we can get the molecular weight of any unknown sample from a mass spectrum. Hope you will like this video, and the next video we will talk about some other aspects of mass spectrometry. So see you then. Bye.